So what we've been looking at so far in matter and radiation are things which slow the universe down. So the Hubble parameter, h here, is 2 over 3t or 1 over 2t. So in other words, as t gets bigger, the rate of expansion decreases. This is a Hubble parameter, remember, it's not the Hubble constant, which is just the local measurement of that. So both matter and radiation slow the universe down. So now let's look at cosmological constant. That is W equals -1. Now this actually is a really easy one to solve, but also a really puzzling one to solve because of the following. If I look at the fluid equation, E dot plus 3A dot over A, E plus P equals 0. P is WE equals minus E. So the fluid equation just becomes E dot equals 0, or E lambda, the energy density from the cosmological constant, is equal to a constant. Now this is really weird when you think about it, because this is an energy density. It's not a total energy. This is, can't write very well today. This is an energy density, i.e. it's joules per cubic meter, or something like that. And so as the universe gets bigger and bigger, you actually get more and more energy out of the cosmological constant. The universe gets smaller, it becomes less important. As the universe gets bigger, it becomes more important. And this is quite a challenge. In fact, I had a question emailed to me last week from someone about how the expanding universe works with conservation of energy. And the kind of answer is it doesn't really work with conservation of energy, and nor does general relativity require it to. But nonetheless, this is a very confusing thing to look at, because the energy density being constant means that the total energy from the cosmological constant as it universe expands gets bigger and bigger and bigger. So we can look at this. The energy density is E lambda. It's always, therefore, the critical density. And this number then has no dependency on the scale factor. So the critical density is a critical value, but it changes as the scale factor changes. So it's fine if you have a flat universe and it gets twice the size, and it's dominated by matter, it becomes 1/8 of the density. The density, is always the same in joules per meter cubed. And here the Friedmann equation very simply, I just substitute in E equals E lambda, so I get A dot squared equals 8 pi G E lambda times over 3c squared. And I can rewrite that, if I like, as A dot equals H A. Sorry, there's an A squared here. So E dot equals H times A. And I'm going to write H naught because it turns out that the expansion rate of the universe is always the same in a cosmological constant dominated universe. So remember, A dot is just dA by dt. So dA over A equals H naught dt, i.e. log A equals H naught t, or A equals the exponential of H naught t. And so a cosmological constant leads to an exponentially expanding universe. remarkable. It's actually an accelerating universe because you're gaining energy as you go. So, not obvious that this is really something that you'd expect to see, but it's allowed, and that's what you would see if it was there.